Fuzzy blobs for electron orbitals.
The spheres, the dumbbells.
Yeah, the dumbbells, the sort of cloverleaf things. But have you ever really stopped and thought, why those shapes, you know?
Right.
What actually dictates that specific geometry inside an atom?
It does feel a bit strange, doesn't it? You sort of expect tiny dots just buzzing around.
Right.
But our source material for this deep dive, it's a great piece called Spherical Harmonics and Electron Orbitals. Makes it really clear the answer is somewhere maybe unexpected.
Okay. Where?
It's in the mathematics. Specifically the math describing how things vibrate on the surface of a sphere.
Vibrations on a sphere, like a drum, but, well, spherical. That's kind of wild.
It is, isn't it?
So, okay, our mission here is to take that idea, electron shapes from sphere vibrations, and really unpack it. We want to show you how these spherical harmonics, that's the term, right?
That's the term, yeah.
How they act like a sort of quantum symphony, laying down the rules for electron shapes, giving us those precise quantized orbitals. The idea is to give you a shortcut to understanding this, maybe spark a few aha moments.
Exactly. And the core idea the material really hammers home is this atomic structure, especially how electrons arrange themselves. It isn't random. It's a direct result of the allowed mathematical patterns for vibrations on a sphere.
So the atom itself has this kind of underlying spherical nature, this quantum sphericity, and the electrons, they just have to follow those rules.
That's a good way to put it. Think of spherical harmonics as the fundamental ways a sphere can vibrate, the natural modes. And it turns out the electron's behavior, at least its angular behavior, its shape, is governed by those exact same mathematical functions.
Okay, but how do we connect an electron orbiting a nucleus to sphere vibrations? Our source brings up the Schrödinger equation. That's the big one in quantum mechanics.
It is. It's basically the rule book for quantum systems.
Yeah.
It tells us the possible states, the possible energies and wave functions an electron can have in an atom.
And the key for atoms is symmetry.
Yes.
Huh.
Particularly in simple atoms like hydrogen. The potential energy the electron feels from the nucleus, it depends only on how far away it is, not which direction. Perfect spherical symmetry.
Okay, spherical symmetry. How does that help with the big scary equation?
Ah, it's beautiful, actually. Because of that symmetry, when you write the Schrödinger equation in spherical coordinates, using distance r and two angles, theta and phi, you can split it.
Split it.
Yeah, you can separate it into two parts. One part of the solution depends only on the distance, or the other part depends only on the angles theta and phi.
Wait, hang on. So the shape part of the electron's description is completely separate from how far it is from the nucleus.
Precisely. And the stable allowed solutions for just that angular part of the equation. Those are the spherical harmonics, denoted yilm.
Wow.
They are literally the mathematical descriptions of the only possible stable ways a sphere can vibrate. The standing waves, if you like.
Okay, so yilm, it's not just abstract math, it is the shape information. That's like a guitar string, right?
Yeah.
It can only vibrate in specific ways to make specific notes.
Exactly. Or the patterns on a drum head when you strike it. Those specific patterns, they're like the spherical harmonics. They're the allowed modes of vibration on that surface.
Okay, let's dig into that vibration analogy more. The source talks about nodal lines. What does that mean here?
Right. So imagine our vibrating sphere again. Like a vibrating string has points that don't move, or a drum head has lines.
Like nodes.
Yes, nodes. A vibrating sphere also has these stable patterns, these modes, and they're characterized by nodal lines, lines on the surface where there's zero movement, where the vibration effectively cancels out.
And these nodal lines, they connect directly to the quantum numbers, L and M.
Directly. Those two numbers, L and M, they just naturally emerge from the mathematics of solving that angular equation. They define the pattern of nodal lines.
How?
Well, the azimuthal quantum number, L, it basically tells you the total number of these nodal lines. A bigger L means a more complex pattern, more lines.
Okay.
It also corresponds to the electron having higher angular momentum. And the simplest case, L equals 0. That means 0 nodal lines.
Ah, so the vibration is just uniform everywhere.
Exactly. Perfectly spherical vibration.
Makes sense. So L is complexity, number of lines. What about M, the magnetic quantum number?
So M tells you about the orientation of that pattern of nodal lines in space. For a given L, a given complexity, M can take integer values from minus L up to plus L.
Okay.
Different M values for the same L represent the same basic pattern, just rotated differently, pointing along the x-axis versus the y-axis, for example.
So these Ulam functions, these spherical harmonics, they're not just an analogy. They are the actual mathematical functions that describe the angular part of the electron's wave function, like where you're likely to find it, direction-wise.
That's the core takeaway. They define the shape of the probability cloud, ignoring the distance part for a moment.
Right, but then if orbitals for L greater than 0 have these specific non-spherical shapes like the dumbbells and clover leaves, why do we often talk about atoms having this overall quantum sphericity? Where does that come from?
Yeah, that's a great question. The material points to two main reasons. First one we sort of touched on,
Yeah.
the L0 case, the else orbitals.
Because L0 means 0 nodal lines.
Right. The corresponding spherical harmonic, y00, it's
Yeah.
just a constant value all over the sphere.
Meaning the probability is the same in all directions. So spherical shape, easy enough for sorbitals.
Yep. Your 1s, 2s, 3s orbitals.
Yeah.
Inherently spherical because of that fundamental y00 harmonic. But the second reason is maybe more surprising. It involves something called Unsold's theorem.
Unsold theorem.
Yeah.
Okay, sounds important. What's the gist?
It's a really neat mathematical result. It says that if you take the probability distributions, that's the wave function squared for all the possible orbitals within a given subshell. So same old value, but all the different m values. And you add them all together. The resulting total probability distribution is perfectly spherically symmetric.
Wait, really? So, like, take the 3 p orbitals. The dumbbell along x, the one along y, the one along z. Individually, they're not spherical, but if you add up their probability clouds...
Bingo. The total cloud you get is a perfect sphere. Same for the 5d orbitals. Add up all their probability distributions with all their complex shapes, you get a sphere.
That's... wow. Okay. So the atom's overall spherical nature doesn't always come from each electron being in a sphere. It can come from the complete set of orbitals in a subshell adding up spherically.
Precisely. And that's a big reason why atoms with completely filled subshells, or even half-filled subshells,
Like noble gases or elements in the middle of the D block.
exactly, why they tend to be particularly stable. That overall spherical symmetry of the electron cloud is a very stable, low-energy configuration.
Okay, this is clicking now. So the quantum numbers L and M, which came out of the math of these spherical vibrations, these spherical harmonics, they directly define the shapes and orientations we see in chemistry textbooks, the whole architecture of orbitals.
It all ties back. The allowed ways a sphere can vibrate dictate the allowed angular shapes for electrons. We can quickly map it out.
Okay, L0.
That's your s orbital, y00. Perfectly spherical. Only one orientation because m can only be 0.
Right, then L1.
Those are the p orbitals.
Yeah.
They come from the LE1 spherical harmonics, which have one nodal plane, essentially.
Giving the dumbbell shape.
Yes, and since m can be nidus 1, 0, plus 1, you get 3 possible orientations. Your px, pi y, pz.
Okay. L2.
That leads to the d orbitals.
Yes.
From the L2 harmonics, which generally have 2 nodal surfaces, more complex shapes.
The clover leaves and that weird dumbbell with a donut one.
That's them. And m goes from -2 up to +2, so that's 5d orbital.
5 orientations. And L3.
The f orbitals. Even more complex, derived from the L3 harmonics, generally 3 nodal surfaces, since m goes from -3 to +3.
7 of them. 7 f orbitals.
Exactly. So the whole quantized nature of it, why only these specific shapes and orientations are allowed, why angular momentum comes in discrete units, it falls right out of the mathematics. It's because only certain standing wave patterns, certain vibrations, are stable on a sphere.
That's the core message from the source, isn't it? This deep, fundamental link. Vibration, geometry, and quantum mechanics, all orchestrated by spherical harmonics.
It's a really elegant piece of physics and mathematics working together.
So we started asking why those funny orbital shapes. We found the answer, maybe surprisingly, in vibrations on a sphere. We saw how the math, the spherical harmonics, and the quantum numbers L and M define these patterns, and even the overall symmetry of atoms. And we linked it all back to the SPDF orbitals you're familiar with. The source material really did give us a great pathway into this, hopefully sparking some of those aha moments about how geometry and the quantum world connect.
It definitely shows how, sometimes quite abstract mathematical ideas end up describing physical reality in a profound way.
Absolutely. So here's something to think about after this. How does really picturing electrons not just as particles or fuzzy clouds, but as specific, allowed vibrational patterns on a sphere around the nucleus? Almost like musical notes, but for probability. How does that shift your fundamental gut feeling about what an atom is and what everything around us is made of?
That's a good question to ponder. It changes the picture quite a bit.